Hi and welcome to Profex Tutorials. In this episode I'm going to demonstrate how we can create Profex instrument configuration files for our own instrument setups. This is often the first major hurdle to overcome for new users because a lot of detailed information on the hardware setup is required. So let me guide you through this process step by step. To get correct refinement results and to reach a good fit, it is absolutely crucial to use a correct instrument configuration. Let's start by using a wrong configuration to demonstrate the problem. This is a scan of a LAB6 certified reference material that was measured on a Panalytical Expert Pro instrument. To create a refinement project, I select Add Phase. I locate the LAB6 phase and I select the instrument configuration used to measure this scan. But instead of selecting the correct Expert Pro configuration, I will now select a Bruker D8 instrument, which is obviously wrong. So let's see what happens when we start the refinement. We can easily see in the difference curve that there is a massive problem with the refined intensities. At low angles, they are underestimated. The calculated LAB6 intensities are much lower than the measured ones. And at high angles, it's the opposite. The measured ones are lower than the calculated ones. So this is one problem we can easily see, but there's more. If we zoom in, we can already recognize that also the shape is a little bit different. And if we use a Lebesgue profile fit instead of a Rietveld refinement, we can match the intensities. I open the LAB6 structure file and I add the keyword Lebesgue 1. I should also refine the unit cell, and I repeat it. Now the intensities are matched to the measured intensities, but we are not using a Rietveld refinement, just a Lebesgue profile fit now. But it allows us to see that the shape is really different. The measured peaks are much more asymmetric at low angles than the calculated ones. So with this configuration, the Bruker D8 configuration used for a dataset measured on a Panalytical Expert Pro instrument, we will never be able to reach a good fit. We will always have intensity problems and also peak shape problems. So how can we get the correct instrument configuration for the Panalytical Expert Pro instrument? I usually prefer to edit an existing configuration rather than starting from scratch with a new configuration because it's a little bit quicker and easier. So to edit the wrong Bruker D8 configuration, I go to the Instrument menu and I select Edit Current FPA Configuration. FPA means Fundamental Parameters Approach. So I select this and it will open the configuration in a graphical editor. And if you don't get this graphical editor and only see a text editor instead, you're probably using an old version of Profex because this graphical editor was introduced with version 4.2. On the left-hand side, we see a tree structure representing the instrument, starting with the goniometer, primary beam path, all the optical elements in the primary beam, the sample stage, and the secondary beam path with all the optical elements in the secondary beam. If we highlight or select one of these elements, it will be highlighted in the graphical representation. We can also click on the graph here and select an instrument, and it will be highlighted in the tree structure. And at the bottom of the tree structure, we see the parameters list for this specific element. So if we select the X-ray tube, we see all the parameters we have to specify for the tube, starting with the type, whether it's a cathode ray tube or a synchrotron source, and the target width and apparent height. And we can also select the file describing the characteristic radiation spectrum for this tube. And we could specify a scan with the tube tails for tube tail correction. If we don't know exactly what we should enter or what these parameters mean, there is also a description on the descriptions page. When we select one of these elements, it will always show the description and some help and additional information. Now we need to figure out the hardware configuration that was used to measure this LAB6 dataset on the Panalytical Expert Pro instrument. And gathering all the necessary information can be rather difficult because we need a lot of detailed information, and sometimes we don't have access to the instrument anymore, and it is usually not very well documented. So let me show you a few tricks where we can get this information from. I opened DIFRAC EVA, which is Bruker's data evaluation software, and now I can load one of my BRML files. It will display the scan, and on the right hand side I see the data properties pane. If you don't see this, you can open it in View and click here or press F3. So in this table I see additional information on the hardware that is stored inside the BRML file, and some of this information we need to create the instrument configuration. In the section measurement conditions, for example, we see the start and end angles, the step size, and the time per step. But what we need is the goniometer radius, which was 350 millimeters in this case. Scrolling further down, we don't need the drive information or the environment information, but wavelength gives information on the X-ray tube. We used a copper anode tube with a line focus, and it gives us the K alpha 1, K alpha 2, K beta radiation wavelength. The generator we don't need, but the detector is important. It was a Lynx Eye XE detector used in 1D mode with a detector opening angle of 2.352 degrees and a detector slit width of 9 millimeters, which is fully open. The apertures are important. It lists the solar slit in the secondary beam path with an opening angle of 2.5 degrees. This one is given in degrees, not in radians. And we did not use the beam knife. The divergence slit was set to a fixed sample illumination of 15 millimeters, and the anti-scatter slit was set to a fixed opening of 3.03 degrees. So this information is very useful to create the instrument configuration in Profex. So let's go back to Profex. It is probably possible to access similar information from Panalytical XRDML files using the software HighScore Plus or Data Collector. But what can we do if we don't have access to these instrument-specific programs like DIFRAC EVA or HighScore Plus? For example, if we are working on a personal computer instead of the instrument control PC. And if we are using modern file formats, such as the XRDML file from Panalytical or the BRML files from Bruker, we can also access the same hardware information without this specific software. And let me show you how to do this for XRDML files. I go to the location of my file here, and this can actually be opened in a web browser, for example Firefox. I can just open this file in Firefox, and it is kind of human readable. It's an XML file structure, so it's got tags and then readable information within these tags. So starting at the top, it starts with a comment section. We don't need that. Some information on the sample, we will also skip that. And then we see the block XRD measurement. And this is where the interesting information is found. Here's another comment section, and then the wavelength that was used to measure the data set. We can see it's 1.45 angstrom for K alpha 1, so that's characteristic copper radiation. Next, we see the incident beam path, and this is a similar description in XRD in XML format as what we need in our graphical instrument editor. So first of all, we see the radius of the goniometer, that was 240 millimeters. Then we see information on the X-ray tube, the tension and the current of the generator, and also the size, the length and width of the target. It's 12 millimeters by 0.4 millimeters with a takeoff angle of 6 degrees. Next, we have information on the solder slit. On the collimator in the primary beam, it was a 0.04 radians opening angle. Then we have a beam mask. It was a fixed 10 millimeter beam mask. So the distance to the sample was 124 millimeters and the effective width of the mask was 6.6 millimeters. Next, we have an anti-scatter slit with a height of 0.38 millimeters. That's obviously a 1/4 degree opening angle. Then the divergence slit was a programmable unit positioned at 140 millimeters from the sample, and it had an opening angle, a divergence angle of 1/8 degree. Then we have a block for the sample stage. It was a spinning sample stage, spinning at 1 revolution per second. And then the diffracted beam path. Again, with the radius, the anti-scatter slit, another solder slit of 0.04 radians, a nickel filter to filter K beta radiation, and the detector was an accelerated detector with an active length of 2.122 degrees. So that was the hardware configuration, and here following that we have information on the current scan, the start and end times, the start and end positions in 2 theta and omega, and all the intensities here. So this is information we need in Profex. You can go back to Profex here. So for the X-ray tube, it said it was a cathode ray tube with a target width of 12 millimeters and an apparent height of 0.4 millimeters. But if we go to the description, it says the apparent height is 1/10 of the effective height of the target. And this has to do with the takeoff angle. So here in the graphical representation, we can see that the beam leaves the target at an angle of 6 degrees. That's the takeoff angle. And if we look at the target from this direction, its apparent height, so distance in this direction, is only 1/10 of its effective height. We can do trigonometry to calculate this. So what we have to enter is 1/10 of the effective height. That's the apparent height, so that's why we enter 0.04 millimeters here. It was a copper tube, that's what we saw in the XRDML file, so we can select one of the copper lambda files here, and we don't have a tube tails scan, so we just leave this empty. So the tube is now set up correctly. Next we have, so we just work our way through this list of optical elements. If we activate the axial slit here and read the description, it says the usage of an additional axial slit near the X-ray tube is supported. But we did not have this. So we had a anti-scatter slit. So we had the divergence slit, the collimator, and a beam mask. So we deactivate this. The divergence slit, we can choose between a variable mode or fixed mode. And in fixed mode, we can choose between either specifying the opening in millimeters and the distance from the sample. So it can calculate the beam divergence angle from these parameters, or we can just enter the beam divergence angle, which was 1/8 degree. So we should enter 0.125, but actually this is a bug, we cannot enter enough positions. I will show how to fix this later on. So we just leave it at that, and we will change this value to 0.125 later on. The primary solar slit was given either in radians or in degrees. Here it was given in radians, and it was 0.04 rad. That's all we have to enter. And then we had a beam mask. I have to check again the values for the incident beam mask. Here it was positioned at 124 millimeters from the sample and an opening of 6.6 millimeters. So that was 6.6 and 124. Another element we don't need, it's a pinhole, so a round hole aperture that's not installed. So we move on to the sample. We have to specify the instrument geometry, if it was a capillary or a transmission instrument, but we were using a reflection instrument in Bragg-Brentano parafocusing geometry, so we choose this. And the sample holder had a round cavity with a diameter of the powder cavity here of 25 millimeters. So we can leave it at this setting. This is the beam knife. We did not use one, so I just deactivate this. And on the secondary beam path, we start with the anti-scatter slit. Again, we have to choose if it was in variable mode or in fixed mode. So let's go back to our XRDML file. In the diffracted beam path, we have an anti-scatter slit set to a fixed angle of, again, 0.125 degrees. So the same problem, we cannot enter enough digits. We will fix it later on. And we had the same opening for the collimator, for the secondary solar slit here. And we did not use a detector slit and no monochromator, so we can move on to the detector. And now we have to enter some data about the CCD sensor in the detector. And if we don't know this, we might find it in the list of presets. So it said it was an pananalytical accelerator detector, so luckily we have it in the list and it will fill in all this data. Else, if we don't find it, the specific model of detector in the list here, we have to enter this data manually, and we have to figure it out somehow, maybe from the manual of the detector. It's usually documented somewhere. So this is the updated configuration. We changed basically, I forgot the goniometer. So if we click on the background from another element on the background, it will jump to the goniometer, and we have to specify the radius, which was 240 millimeters. We found it, for example, here, the diffracted beam path, the radius was 240, and also the same for the incident beam path here. So now the configuration is updated to the pananalytical instrument, and we can save it under a new name. And then we need to start the calculation of the peak profiles by clicking the button on the bottom left, Run Calculations. But before we actually run the calculation, we need to fix something. Remember, we had the wrong values, slightly wrong values here for the divergence slit, beam divergence, and the same for the anti-scatter slit in the secondary beam path. So I want to show you how we can override settings here in the graphical forms by editing the instrument configuration text files. So here on the top right corner, we have a few buttons. The one on the left says Show Graphical Editor. That's the mode we are currently working in with the graphical instrument editor here. The next button says Show Control File Text Editor. So if we click this button, the configuration we set up here in the graphical display will be converted to the BGMN instrument control file format. So now we see the text file as we had to edit it in previous versions of Profex. And we can still modify it, so we can scroll down to the divergence slit, to the beam divergence, and instead of 0.12, we add 0.125 degrees beam divergence, and the same for the beam divergence of the anti-scatter slit. Now, if we edit something here and we go back to the graphical editor, we will see a warning that some of these edits may get lost. So do we really want to continue? If we say yes, you can see that it now changed. So it rounded up to 0.13. So the edit was lost again, and it was converted back to two digits. So if we don't want these edits to get lost, we have to stay here in this. So we have to do the modification again. And we have to stay in the text editor and run the calculation from here. So now this file will not be modified anymore. Whatever we change here will be used for the calculations. And now the computation of the profile shape started. And this is a very slow process. It will take a few minutes to complete. So we will fast forward. That's it. The computation of the peak profile is done. So we can use the new configuration now. And I will open the same scan file again. Create a refinement project with the LAB6 phase. And this time I should be able to select this new configuration from the list of instruments here. And we start the refinement. And as you can see, the difference curve looks much better. If we toggle between the previous, this was the Bruker D8 configuration, and the new Expert Pro configuration. If we zoom in, we can see a very accurate fit of the asymmetry of the peak shape and a tiny mismatch at the very top. And this is a pretty usable configuration with only minimum difference between the observed and the calculated profile. I mentioned before that we can not only open XRD files like this, so the Panalytical file format, but also Bruker BRML files. But it works a little bit different. We cannot immediately drag them to a browser. This is not going to work because BRML files are actually compressed archives. So to access the XML files inside this archive, we can simply change the extension to zip. And now we can extract them. It's just a zip archive with a bunch of XML files inside. So maybe we go back to BRML just to avoid confusion. And now this is the content of the BRML file extracted. And inside we see experiment folder. We go to this folder. And now we have one file called rawdata0.xml. And this file we can now drag to a web browser, just as we did with the Panalytical file. And it looks very similar. It's the same kind of structure, XML structure with tags and all kind of readable information. And it's just a different kind of structure, so it's not exactly the same as the Panalytical files. We have a long list of so-called datum tags. These are the measured values with angles and intensities, and we want to skip this. And at the very bottom, we find information here, instrument information, and this is what we are looking for. Inside the instrument tag, we have a tag primary tracks, that's the primary beam path, and then we find information we need. For example, the radius of the instrument was 350 millimeters, and the mounted optics, it starts with the tube on bank position 1. Again, information very similar to the XRDML file we saw before. Generator settings. Then on bank position 2, here we have a motorized slit with a set to in mode fixed sample illumination with a value of 15 millimeters sample illuminated length on the sample. Bank position 3 was empty, no slit. Bank position 4 contained the actual solar slit, the 2.5 degrees. This is in degrees, not in radians as before. And then we have the secondary track starting from the end, so from the detector side on bank position 18, we have a Lynx-Eye XE detector, an open slit position, another open slit position, a detector slit set to 9 millimeters opening, again the actual solar slit, 2.5 millimeters, and an empty slit bank, and on bank position 10 the motorized slit set to a fixed opening in degrees of 3.03 degrees. So we can access the hardware information in Bruker BRML files in a very similar way as we did with the Panalytical XRDML files, only we have to extract the archive first and then open the file raw data 0.xml inside the experiment folder. If you don't find a way to extract the necessary hardware information from the raw data files, for example using the tricks I've shown before, or using the software from the manufacturer, then you probably need access to the instrument, and you need to figure out the configuration by having a look at the optical elements. For example, the old slit apertures usually have their openings printed on the aperture. Like in this case, at the top, that's a divergence or anti-scatter slit of 1/8 degree opening. Or at the bottom, we see 3 different beam masks with the opening printed on the element. In the middle, this is a solar slit, and somewhere on this unit, we will also find the opening angle in either degrees or radians. Next, we may have to take a ruler or a caliper and measure distances from the sample to the positions of the slits directly at the goniometer. It's not super accurate, but it's usually good enough for what we need. I hope you enjoyed this episode. Don't forget to like this video and subscribe to the channel, and I will see you soon.